Yeah, no problem. Thanks as well for mentioning that. I think that's probably at least the second time a weird due date came up like that. Okay, so this one is due August 4th. That looks about right. So that would put this one, assuming we complete on Thursday, that would be due August 4th as well. Well, looks like we can start officially. Again, welcome back, and thanks for mentioning that weird due date issue there. As for pretty much all the assignments, just to reiterate comments we mentioned before, any work that does go late, even if it was a weird due date there, those should all get fixed. But anything that did go late, I'm accepting for full credit. There'll be a cutoff date for that because the semester, let's see, Friday, July 31st, that was a error there as well. My cutoff for the final day for any late homework should really be Friday, August 7th, because that's considered to be the last day of the semester. We meet on the 6th, we'll be meeting on the 5th for review, on the 4th for review. Thursday is going to be the official day for the final exam, so we won't meet on that day, but I'll still have office hours. And the last day to turn in any late work should be Friday, August 7th. Let's fix that one as well. Other thing that's new after that revision there, that double period's gonna annoy me. Let me fix that real fast. Other thing that's new is this extra credit opportunity. This is not something that you have to do to get the opportunity. This will apply to everybody. In the syllabus, it said that the lowest two homework assignments will be dropped. I feel like for the pace of this class, doing it in just 8 weeks, the fairest thing to do at the very end of the semester will be to drop the lowest 5 homework assignments. So that's what we're going to be doing at the very end. So if there's any assignments that you got a little bit of a lower grade than you wanted to, any kind of off days you might have had, I'll be dropping the lowest 5. And aside from that, those are the major comments I wanted to start off today. The final exam, like we mentioned, will be on Thursday of next week. That'll be the official day, but there's a range of dates you can take it. It can be taken early. Some people requested to take it on Friday of this week, but for I think the typical people, it'll be taken between Monday the 3rd and Friday the 7th is a good suggestion of time. I would say go for Thursday because we're going to have a review on Tuesday and Wednesday to end the semester on. So if you can make it happen on Thursday or Friday, those would probably be the better days. But any questions or comments at all then before we get started? Okay, well, let's jump back in. We're on the second half of section 5.5, dealing with the substitution rule. And we mentioned before, Calculus 2, if you're taking that course, hits the ground running on more integration techniques. It doesn't really launch off these topics here in chapter 6. We're doing these as applications to the definite integral, really more practice for us on integration. What it will launch off is going beyond the substitution rule to the next so-called technique, integration by parts. And so being really fluent in sections 5.3, 5.4, 5.5 is really fundamental to get a really good start on Calculus 2 if you're taking that course. So we'll go back here, solve some more problems carefully. And then when we start chapter 6, our goal is not to race through these topics, more focus on the concepts and extra practice on integration is going to be the main takeaway on any work we do in chapter 6. So let's jump in. Here's our substitution rule for definite integrals. And essentially, all we're really using to make this work happen right here is the idea of the differential. Let's rewrite it over here just for a quick reference. If u equals a function, say g of x, I guess it's already defined right there. Then the differential of u is du equals g prime at x dx. So that was our major concept to make everything happen in the first half of the notes. If we use the differential just right, we can transform from a complicated integral like we see here to a much more streamlined, easier to find an antiderivative integral here on the right-hand side. If it's a definite integral, we'll still use the differential in the normal way. Essentially, the only new things are we're changing the limits of integration, and for the definite integral, we do not have to undo the substitution. We can stick with the new variable u to finish off the problem. So that's our major idea. That's the same color coding as we used before. And now let's try it again on this problem here. This one's not too bad of a problem as far as they go. So we're going to use this one as kind of a warm-up in using the u substitution here. It's a function cosine with another function. It's a linear function of the variable t, pi halves t. If it was just cosine t, that's not too bad to find an antiderivative on. And honestly, this one's not too bad to find an antiderivative on either. But just for the sake of practicing this rule here, let's do this from very first principles. First thing we're going to do is pick a function for u. We're undoing the chain rule, which is all about function composition. So we think once again in terms of what's the outer function, what's the inner function. Outer is cosine, the inner function is pi over 2t, and that's often a good choice for your function u. So u is going to be pi over 2 times t. The immediate thing we go to next is differential du. Du then becomes, take the derivative of this function, it's linear degree 1, so it just becomes pi over 2, times dt. Not dx, dt here just to match the independent variable t. Then we have the same conundrum we've come up before here. dt does occur, so we can make a substitution on that. But there is no pi over 2 inside this integral. It's trapped inside the cosine function, but it's not multiplying as a coefficient inside the integral. We can't do anything with that pi over 2, it's just trapped there. In fact, we're going to swap it for u, so it has to stay right exactly where it is. And so our next fundamental technique here is, if we're off by a constant like, say, pi over 2, we could just rearrange that differential, rewrite it as 2 over pi du equals dt. In this step, we just divide by pi over 2, which means multiply by both sides by 2 over pi. And that's what we'll replace the dt with, 2 over pi du. So everything's set up. We're going to throw a u inside a cosine. That'll be easier to visualize the antiderivative on. New formula for dt. The only thing that does have to change now is limits of integration. Going from 0 to 1 was only relevant for the variable t, but we have a new variable u in the picture, so we make these changes. We're going to say if t equals 0 or t equals 1, this will then imply change these values to the new variable u. What we'll do with u is just plug in the value of t. So plug in 1 here, that's just going to be pi over 2. Plug 0 here, and we just get 0 altogether. So same lower limit of integration, but a new upper limit of integration. We're now going from 0 to pi over 2. And it's a good idea, again, worth mentioning, be very careful when you write down these limits of integration. Copy them in the same order, upper limit, lower limit. Same order here, upper limit to lower limit. Same order as you find the values for u, and then plug them back in the same exact order. If we swap those at any point, we're probably off by a sign. So this becomes an integral. Actually, let's give this a little bit of space before writing the integral sign. We're going from 0 to pi over 2. So those are our changed limits of integration. This will be cosine of u now. dt, we have a formula for that. That's the rearranged differential here on this line. We're going to write it as 2 over pi du. But this 2 over pi, the other trick we use is, because it's a constant, we typically write it way outside the integral here. 2 over pi. Not required, but it allows us to focus on the integrand cosine u, not multiplying by the constant, 2 over pi. du gets put in, so now we're integrating cosine u with respect to the variable u, is what du says. And this one is a lot easier to visualize. This isn't the worst problem we've done in the notes so far, but again, think of this one as a good warm-up using these rules. And it's usually a three-stage process. Step 1, pick your u. Step 2, do the differential, rearrange it if you have to. And step 3, substitute everything back. Change the limits of integration if it's a definite integral. Once we get here, the goal is we're now solving this kind of integral, and it should be way easier than the original. Any questions or thoughts getting to this step? Okay, let's go to finalize this. The result is now 2 divided by pi will be multiplied by antiderivative of cosine u. That's just going to be sine, because the derivative of sine becomes cosine. So we'll multiply that by sine u. We're integrating the whole thing from 0 to pi over 2. But since this is just a constant multiplying, when we evaluate, we can leave the 2 divided by pi just factored out to the left. And a lot of times that's a good time-saving step right here, especially if it involved a negative sign, because you're going to have a negative there, and you could end up with double negation. It's easy to get a little bit mixed up on those negative signs. So keeping the constant on the left factored out, just like it was on the left here on the definite integral, is a good time-saving step. So now fundamental theorem of calculus has been applied. We just need to evaluate this antiderivative. So it'll be 2 over pi, evaluated at the upper limit, sine pi over 2, minus evaluate at the lower limit, sine 0. Because that's a variable u, and we transformed the values of u to those two values, we're allowed to substitute in and never undo the original substitution u whatsoever. Also means our work is just about done. We just need to evaluate our trig functions. Sine of pi over 2 is 1, sine of 0 is 0. So this is just a glorified 2 divided by pi times 1, with the overall result of 2 divided by pi. So that tells us the antiderivative of cosine pi over 2 times t from 0 to 1 is just 2 over pi. Where I said the antiderivative, let me say that a little bit better. The area under the graph of the cosine function from 0 to 1 is 2 pi altogether. Well, that's the review of our techniques so far. Any questions on getting through this one, start to finish? Okay, well, our goal for the rest of these notes is just to practice a few more, just to get some good work under our belt on dealing with these. You'll practice very similar kind of problems as well in the homework assignment. So our next one to take a look into is going to be this one. Probably deserves a new page. Doesn't look like the most friendliest antiderivative or integral problem to deal with when we look at this one, but really it's not too bad if we can get to right u in the u substitution process. We mentioned before, sometimes there's a little bit of trial and error involved in this. The reading in the book, the author says it's sometimes a little bit of an art to pick the right value for u. One thought is, if you pick it wrong and you can't get the substitution to go through, don't worry too much, just try to pick it in a different kind of way. You could go small, picking u equals x, but oftentimes that's not going to give us much. That's just changing the name of the variable if you pick u as x. Going as a bit of a larger function, you could pick u equals that entire thing, x times the natural log of x. That's getting really complicated, and the derivative of that needs the product rule. So we want to find kind of a middle ground. We don't want to pick u as just the variable x. It's just changing the variable. Integral is just as hard. We don't want to grab a massive function like that whole thing. If we can find a good middle ground, it's a good place to start. And there's not one and only one method. Sometimes there's multiple methods that could work. A good strategy that we mentioned before is if you see a function inside of another function, that's not a bad idea or a bad choice to take. Here we see the natural log x is inside the square root function. So with that function composition, if we grab the inner function, that might not be a bad choice. It's not the only choice that works on this one. But let's give it a try, see how it goes. So let's let u equal the natural log of x. So that's our choice for u. This may or may not work out. Only way to know for sure is see what happens when we take the differential. Differential is going to be du. We take the derivative of natural log x, which is a 1 over x, multiply by dx for the full differential, and then analyze what we have inside the integral. We definitely have the dx, so that's going to help us out. This is 1 divided by x, and we could factor out that x as 1 over root natural log x times a 1 over x. So if you see an x in the denominator like this right here, that tells us we can substitute out 1 over x just immediately in the setup here. That's great because then there's nothing left over. Everything gets changed over into the variable u. So this substitution will in fact work. It's not the only one that works. It turns out you can let u equal the square root of natural log x, and then that one also works. So if you want to try it in a different way, give it a try going that way. Work looks different, but we're going to get the same exact answer. But we're making some progress on this one, so let's just keep it as u is natural log x and see what happens. This is a definite integral, so the area is an answer, which means we can change the limits of integration on this one. These lower and upper limits are for a variable x. So we have x is e power 4, x is e or e power 1. This will then imply u, the new variable. We throw in those values for x inside the function for u. U for the upper limit is going to be the natural log of e power 4. For the lower limit, u is going to be the natural log of e, or you could say e power 1 if you like. And these are kind of convenient values. They looked kind of awful to start the problem to have base e exponential for the lower and upper limit. But over here, we can see how that's actually kind of convenient because there's a cancellation going this way and this way. And this tells us the values for u are going from 1 to 4. So that's how our limits of integration will transform on this one. If it's e to e power 4 and u is specifically that substitution, we're just integrating from 1 to 4 altogether. So those are our 3 stages. There's a lot of analysis right here just to get started on this kind of problem. And then it's just the mathematical idea of make substitutions. The integral is now equal to, substitute in place of e power 4, 1 to 4, so we're integrating from those values. Then we have a fraction. This is now 1 over, let me change the color here. This is 1 over the square root of, let me write that square root slightly differently. It's a power 1/2 really, of natural log x, but natural log x is just now a variable u through our original substitution. So that's u to the power 1/2. What's remaining is a 1 over x times a dx, but that's just a du altogether. So we throw in du. through the differential formula. And our work isn't over, but the original integral we had to solve is a complicated looking one. What our work allows us to do is to take something that's really a section 5.4 type of problem and reduce it to what's now a section 5.3 problem when we saw the fundamental theorem of calculus for the first time. So that's pretty much the theme to a lot of techniques of integration. Take something complicated, reduce it down to something familiar, and even in Calculus 2, we're bringing things back to section 5.3 as much as we can with our substitutions and our methods. So we can integrate that. That's going to be our next steps. Any questions to get to this stage right here? Okay, if this was, say, a 5-point problem, either on a homework or, say, on the final exam, I would say getting to right here where the red dot is, that should be about 3 points out of 5, because that's where a lot of the major work goes here. Remaining points is just to do the evaluation, get the exact area. So on the next step, let's rewrite the integrand in a form just easier for us to deal with. We're integrating from 1 to 4. The function can be re-expressed as u to the power -1/2 du. So this is now more amenable to integration. We can get the antiderivative by reversing the power rule. We add 1 to the exponent when we find the antiderivative. So this will be plus 2/2 to give us a 1/2 altogether. Divide by 1/2 means really just multiply by 2. Put a little parenthesis here since I want to leave that 2 factored out on the left-hand side to simplify the next steps. Then we take all this, evaluate it from 1 to 4. 2 is going to stay on the far outside to simplify the next steps. And here's what it's going to look like. 2 is out on the left. Plug in the upper limit of integration. That'll be 4 to the power 1/2. But at this stage, it's easier to visualize it as square root of 4, really. Then minus, throw in lower limit of 1. That'll be square root of 1. So this becomes 2 times square root of 4 is 2. Square root of 1 is 1. So 2 times 2 minus 1, that's just a 2 times 1, which tells us the area under this really complicated looking function from e to e power 4. Those very specific numbers will give us an area of exactly dead on 2. We've done it. That's another tricky integral for us to get through. The first one was kind of a warm-up. This is one where really, I would say u substitution is the typical thing pretty much everyone would use on for this kind of problem. Any questions or thoughts getting through this one? And bear with me for a moment. I forgot to load in a calculator. Okay, now that the calculator is loaded in, maybe last thought on this one. If you're doing these on the homework and you want to just get a reasonable idea of how close these values are to being correct, you can just plot the function. It's y equals 1 over x square root natural log x. You want to give it the right domain. So this is as we go from e less than or equals to x less than or equals to e power 4, which is a pretty decently big number. And here's the graph. Let me see if I can kind of fix my window a little bit better. Not an easy one to visualize, but if we fix our window, let's go from the y-axis of, let's say, value -1 to maybe 0.1, about 0.2, about like that. It seems reasonable that this should have area about 2 under this graph. It's definitely positive, so we know that. There's a good amount of area to start off, and then it really approaches the horizontal axis rapidly. So if this looks visually about like area 2, it's kind of hard to see because my axes are non-equal, but it gives us some visual check, so numerical evidence that we're on the right track with that number there. So it's kind of small, even though the horizontal range is very, very long, but that's because it approaches the horizontal axis rapidly. If this number came out negative, by this graph, we would know something went horribly wrong, and we have to figure out where the mistake might have happened to be. But let's give this a try. Next one on the notes takes us back to trigonometry, so we'll have a good review on trig just on its own, getting through this problem. We're going from pi over 6 to pi over 2 of the function cosine theta divided by sine cubed theta d theta. So this is kind of an interesting one, now focusing on trig. If you have trig functions like cosine theta, sine theta, really our best shot on this one is our u in u substitution. It should either be the cosine function or the sine function. There is a function composition inside of here. That's really a power 3 function, and then on the inside of the cubing function, sine is on the inside. So that would suggest maybe a good substitution is just sine theta on its own. That's because sine theta is inside that function. If you go with u as sine theta, then the differential du would be derivative of sine, which is cosine theta, and then d theta. Tells us we're on the right track because we in fact have a cosine theta, d theta. These multiply together, give us the right values. So if we pick u as sine theta, power 3 will be ignored, so we're going to have something cubed when we make the substitution. Everything else in the integral can be substituted out, and this looks like it would do the job for us. If we picked, say, differently, suppose you did pick u as cosine theta, then our differential du would be derivative of cosine, which is negative sine theta, d theta. This one wouldn't be on the right track, and the reason we would know that is, although there's a sine theta in our integrand, it's in the denominator. For this to work, we need a sine theta that's up into the numerator. Sure, you could multiply by sine over sine, leaving sine power 4 in the denominator, and then you get sine theta d theta, but that's starting to make this really complicated. Even though sine power 4 could be written in terms of cosine, it feels like you're really kind of putting in a lot of algebraic steps, and it's just getting more and more complicated as you go. Tells us this one is probably not going to be the one that works. So try something else. Just go to the other function sine theta. I'll leave this here just to say it was an attempt, but it did not work. And it's typical of u substitution to try something out. And then if it doesn't pan out the way you'd like, if it feels like you have to get extremely creative to force that u substitution to work, try something else. And even if this is on an exam, say you're taking the final exam, you're not sure how to get through it, if you show me what you've tried, this is worth partial credit. So even if you don't complete the entire integral, you leave your attempts on what you try to pick as u, that's telling me you know how it works. Maybe you just didn't find the way to unlock this one. So don't erase everything, leave your attempts on paper, and it is worth partial credit in an exam situation. So color coding this back to the way it was, we pick a u as sine theta, we get u cubed right there. Cosine theta d theta turns into du. Only thing we now need to deal with is pi over 6 and pi over 2, those limits of integration, we'll change them up so we don't have to undo the substitution, which saves a lot of steps. Well, so next step, the original variable was theta, so we're going to say theta went from pi over 6 to pi over 2. So keep them in the same order like we mentioned before, because we never want to swap them on accident. We'll be off by a sign. If those are the values for limits of integration, we take theta, these theta values, plug them here where our original substitution was made. U is now going to be sine pi over 2 for the first equation. U would be equal to sine pi over 6 for the second equation. So we have to do these evaluations here. Sine at pi over 2 comes out as exactly 1. And at pi over 6, this one comes out as exactly 1/2. So those are going to be our new limits of integration. There'll be a couple places on the final exam where you have to do some trigonometric evaluations like these. So if you feel like that's something you need for the notes, just a couple ideas, some extra information there to help out, that'd be good to have ready to go. So now putting it all together, let's return to the original integral. We're going to integrate from 1/2 to 1. So that's our first swap, limits of integration change. Cosine theta d theta, those are going to be rewritten as a du. So let's put that in first. There's still a fraction here. It goes 1 over. It's sine cubed theta. If u is sine theta, the whole thing turns into just a u cubed where you see it here. So that's our brand new integral. The original one is really mysterious. I don't think we've ever differentiated a trig function and got a cosine divided by sine cubed theta. So finding an antiderivative feels like it's going to be a lot of hard work. If you change variables, it now just boils down to finding antiderivative of 1 over u cubed, and that one is not nearly as bad. So we're on our way with this. This is where the major credit is to get to that stage there. Any questions up to this point before we go beyond to finalize it? Okay, well, here's the next step I would take for this one. If you want the antiderivative of 1 over u cubed, good idea to bring that base up into the numerator so we can visualize how the exponent changes. So this would become equal to integrate from 1/2 to 1, the function u power -3 du. Whether we're differentiating or finding the antiderivative, that's always a pretty good little trick to take. If we were differentiating that, definitely don't use the quotient rule. That's a lot of steps. You can just rewrite the function in this stage. But as an antiderivative, the power goes up by 1. So now this is u to the power -2. You'll divide by -2. So -1/2 in front. But we want to, like we've done on the prior problems, leave that -1/2 right where it is to be efficient, not get mixed up on the double negation that would come up, and only evaluate u power -2 from 1/2 to 1. So there's our whole entire antiderivative. -1/2 gets written twice, but it saves time, makes us more accurate to leave it factored out to that step. And on the next steps, it just becomes -1/2 here, plug 1 inside this function. So this will be 1 to the power of -2, or you could say 1 over 1 squared if you make that exponent positive. And go minus, do the same thing. We're plugging 1/2 inside of there, which means if you force that exponent positive, it's really 1 over u squared. It becomes 1 over 1/2 squared altogether. And this is the side of the problem where it's all arithmetic from here. We'll simplify it down, get an answer, and be on our way with this one. So next steps, it's -1/2, 1 minus. Here, 1/2 squared is 1/4. So this is really just 1 over 1/4. So it's -1/2, 1 minus. The reciprocal of a fourth is 4. So this is -1/2 times -3. That would give us exactly +3/2 altogether. So from pi over 6 to pi over 2, the area under this complicated function is exactly 1.5. It's kind of a mysterious, rounded off nice number. That's only because the limits of integration were irrational numbers to begin with. That's how we're coming up with kind of a nice, well-behaved area, 1.5 really. So we did it, folks. That's really our last one on the official set of notes for u substitution. I wanted to do one extra problem just for one extra bit of practice in a different kind of function that we haven't seen on these notes so far. But any last thoughts or comments on getting through all of these at the moment? Okay, well, again, just for the sake of extra practice, let's try out this new one here. This one's not on the official notes, so let's just call this extra example. I'll just say here briefly, integrate. We want to integrate this thing from a lower limit of 1 to an upper limit of 4, and the function is 3 to the power square root x divided by square root x. So that's our extra example. It's a tricky one because we've dealt with the base exponential, we've dealt with the logarithms, trig functions, and otherwise, but this one is a different kind of exponential function. So it's kind of a review problem in its own right. To handle this kind of thing, here's something I'd want to be ready to go with on pretty much any exam at this point, whether it's the final exam, exam 3, and so on. Have these formulas ready to go. The derivative with respect to x of a base a exponential to the power of x is a to the power of x divided by the natural log of a. So that's our derivative formula. The next portion is if you take the antiderivative of a to the power of x, this is written now in the section 5.4 notation for antiderivatives, but same kind of idea from section 4.9. Antiderivative of a to the x is going to be a to the x divided by natural log a plus a constant. And the reason for that is, if you check your answer by differentiating, when you differentiate a to the x, hang on, I noticed a typo here. When you differentiate a to the x, you don't quite get this. Let me fix this here. You get a to the x multiplied by natural log a. Hang on, let's backtrack off of that. And don't put that formula on the notes, scratch that out. Make sure it's a to the x natural log a when you go to differentiate. Highlight that part for emphasis there. So that's the differentiation formula. I got them backwards in my mind, it looks like. And the way we know the integration formula, we can come back to this one. The way this one works is when you differentiate a to the power of x, you get itself times the natural log a, which cancels with that natural log a that's engineered to be in the denominator for a clean cancellation. So these are formulas to be ready to go with for the final exam for sure, in case these kinds of exponentials come up. But it's still a tricky problem because it's also a U substitution problem at the same stage. But these are the formulas with that correction there. Watch out for that correction to be ready to go with. Any questions about the formulas before we launch through the problem? Okay, coming back over here, there's different choices you can make for your U substitution. You can make it be, say, square root of x. You might try to go big, 3 to the power square root of x, or make u be that whole function and differentiate it, but that's going way too big to be useful. If u is that whole function and you differentiate that, that's the quotient rule, it's just going to be more complicated than it looks like here on paper. So don't grab too much when you pick u. Try to find a good middle ground. What we could try maybe is, let's try a larger thing to grab this time, see if it works out. If it doesn't work, we'll just scratch it out and try again. It's part of the process, sometimes trying more than once. Let's let u be 3 to the power square root x and just see if that works out. If u is that, then we can say du, let me use the same exact color coding as before, du is going to be the derivative of this function. That would be 3 to the power root x, natural log 3, times the derivative of the square root of x. Then we would have to multiply that by dx. Hang on, I usually keep that all in green. I'll fix it on the next line. So du is going to be 3 to the power root x, natural log 3, When we take the derivative of a square root of x, it goes down to the denominator with a factor 2 times the root of x. And that's another handy formula that we cited way back in chapter 3. Let's also state it here. Derivative with respect to x, so square root of x. We mentioned this is just a nice shorthand formula, is 1 over 2 root x. So that's what it would look like all put together. Let's put dx there. It's kind of a mess. There's a lot going on. There's the natural log 3 divided by 2 constant. Then there's 3 to the power root x divided by root x. But that's exactly what we have in our integrand. This is kind of weird. It doesn't look like this should work, but for this particular problem, that would work as a substitution. I think the normal approach is usually u equals square root of x, and that one should work as well. But sometimes when you go a little bit larger like this one, the downside is the derivative is a little bit more work, but it's going to make this integral as simplified as feasibly possible. We should rearrange our differential equation here because there's no natural log 3, there's no divide by 2 inside that integrand. So if we rewrite it, we can say take du equals, we're going to divide by natural log 3, multiply by 2. So go 2 over natural log 3 is going to be equal to 3 to the power root x over root x dx. So looking at what we have here, that whole entire thing, 3 to the power root x divided by square root of x times dx, that is going to turn into this du right here. So that's a kind of a nice simplification. Any questions at all making this differential u work out? Okay, other thing we still want to resolve is limits of integration on this one. We're going from 1 to 4. We don't want to undo our substitution if we don't have to. And this is the case we don't have to, a definite integral. So let's say when x equals 1, and let me keep the order, top and bottom the same. Let me put 4 here, x equals 1 here, so I don't swap them on accident when I bring them back. If those are the values for x, then we can transform u into these values, take values of x, plug them inside. U is going to be 3 to the power of square root of 4, which is then 3 squared, coming out as a 9. On lower limit, this is 3 to the power of square root of 1, which is 3 to the power 1, for a value of 3 altogether. So the 1 and 4 turns into go from 3 to 9 instead. And essentially, all of the work on this one is almost completely on the right-hand margin, all of our preliminary analysis. When we bring it back, there's almost nothing to do with the new integral. That's how you know you picked a really good u substitution on this one. So this one can be rewritten as integrate from 3 to 9. Everything here in blue, following the color coding, turns into this. This time I'll leave the constant inside the integrand because there's nothing else there, might as well. 2 over the natural log 3 du. And that's a pretty fast integral to compute. You don't even really need to take the antiderivative of this. This is a constant function, which means it's going to be the area of the curve, that constant, multiplied by the length of this interval, which is 6. So the answer should just be that function times 6. So 12 over natural log 3. So if you want to answer the question in those kinds of ways, whenever you're integrating a constant, it always goes that same exact way. But if you like finding the antiderivative approach, we could do it that way. Let's do it that way just to show what it looks like on the notes. Antiderivative of 2 over the natural log of 3 is 2 over the natural log of 3 times the variable u. So there it is. I want to use times in this notation, rather, just using parentheses. We're going to take just the function u, leaving the constant factored out, evaluate it from 3 to 9. So if you do that, you'll notice really all you're doing is finding the length of the integral of integration from 3 to 9. because we'll write in 2 over natural log 3. I don't know what happened to that 3. Let's try to backtrack on that. Plug in 9, then go minus, plug in 3. There's where the 6 comes from. And so we get 6 times 2, natural log 3 for 12, natural log 3. So for a really complicated exponential like this one, area under this curve from 1 to 4 comes out as the positive 12 natural log 3 altogether. Well, this is one way to do this one. It's not the only way. So if you did this approach, letting u just be square root of x, this side gets a little bit nicer. The derivative isn't as complicated. This side gets more involved. There's more to do, different kind of substitutions to make, but everyone's going to land at 12 over natural log 3. So all roads lead to Rome. If you can make this substitution work, you're not going to get a different area answer. Well, we did, folks. That's the extra example, just for the sake of extra practice, also to kind of review some of these formulas along the way as well. And at this point, we're done with our integration techniques. And we're about ready to turn over to chapter 6, looking into applications of integration. We'll have the rest of today, tomorrow, and just Monday of next week to look into topics in chapter 6. Then we're turning over to reviewing on both Tuesday and Wednesday for the final exam. But any last questions or thoughts before we close out these notes? Okay, well, let's jump into the last chapter for the whole course. Congratulations on getting through all this so far. We're very, very nearly there, the final week of the entire course. On our syllabus, we said we're going to go from section 6.1 through 6.5. But with our limited time, I don't want to try to rush through any of these sections. It makes it less valuable. We might end up around at the end at 6.3, possibly skipping to section 6.5, which is a nice shorter section if necessary. So we'll see where we end up without trying to rush through these topics. As far as the due dates go, these are always 2 class periods away from when we finalize, and I'll push the due dates as needed, depending on where we end up on. So we're in now section 6.1. We can think of section 5.3 as finding the area under one single curve. And our first application of integration is extending that to finding areas between curves, then going to volumes and volumes through a new technique. So first, here's areas between curves. Oh, didn't mean to minimize it. Here it is again. Okay, and here's our definition that's going to get us started on this one, and a quick little visual example down below. What we're trying to do this time is, instead of finding the area under a curve, find area between 2 curves. For example, here, our f of x function that didn't print out completely nicely. This is y equals square root of x is one curve. On the example below, here's y equals g of x. I printed that in red. I usually don't like to go with red. Makes it look like we made a mistake, but let's keep the color coding the same just for the sake of matching the diagram. Here's a lower curve, y equals x over 2. Now, if we want to find this shaded area between the 2 curves, we can really just restart from very first principles and define the area in this way. The area A between the functions f of x and g of x is going to be the limiting value of the sums of the approximating rectangles. So we have a picture here where I think of this is about, I forgot how many that was. We don't want to count them. Looks like about 40 rectangles altogether. It'll be f at xi star minus gi star. These are sample points coming from out of the ith interval times the widths of all those rectangles, delta x. And we allow the limit to go infinity on those. And we're just looking at a brand new Riemann sum. So that's how we define the area between the curves. We're really just looking at how we did this in section 5.2, sections 5.1. We define the areas in this way. But the major idea with section 5.2 is this should just be equal to the integral as we go from, say, in this diagram, 0 to 4, as a formula, it would be from a to b, coming from these points here, of the function f of x minus the function g of x dx. If we have a limit of a sum like this one, we're dealing with the limit of Riemann sums, and that's just the definition of this kind of definite integral. So when we say applications of integration in chapter 6, this is the major application, that we can take anything that looks like a Riemann sum like this and compute the limit by re-expressing it as a definite integral, and then using the fundamental theorem of calculus, part 2, once again, to solve that definite integral there. In this kind of analysis, we think of the y equals f of x function as being the upper function. Upper because it's the upper bound for the area that we're trying to find of the region S. And we think of the g of x function as being the lower function. So that's the idea. If we can just integrate this, we'll find the area between the two curves. Well, any questions or comments thinking about how the area formula comes together? Okay, well, again, this is our big application for this section, areas between curves. And theorem 2 says this is really all we're doing to evaluate these areas. The area is going to be the definite integral of f of x minus g of x from a to b. What we require is the region A is going to be bounded by the functions f of x, g of x. As we go from a to b, f and g are continuous functions. And since f of x is the upper function, it should be greater than or equal to the lower function g of x for all values in that interval from a to b. That's exactly what we have in this diagram above. And so maybe before we go on to the next questions, let's calculate this area just as a demonstration using that theorem and see what it would come out as. So let's do this computation right here. Area will be the answer to integrate from 0 to 4 in this diagram. We find the upper function, the upper bound, that's just going to be the square root of x. Let's write that in as x to the power 1/2 to make it easier to integrate. Then we subtract. And then we're subtracting the lower function, g of x. But maybe before we subtract, here's part of the logic as well on why we use this formula. If we just ended the whole thing like this, integrate from 0 to 4 of x power 1/2 dx, I'll erase this part right here in a moment. What that would say is we're finding this area, going all the way to the bottom like that. That's more area than we really wanted. We wanted the area in the middle, so we would have to subtract off the area that goes like this, minus the area from 0 to 4 of the excess, x over 2 dx. That's the red line here. That's the area we didn't want. But then you can just combine these integrals into one, and that's all this formula is really doing for us, giving us a one-step shot, so we're not solving two separate integrals in this kind of way. We can just put them together. Sometimes it's a good idea if the term simplify, for example, reduces a lot of the work. So instead of just ending right there at x over 2, we subtract off. Oh, I deleted too much here. We subtract off the x over 2. So I'll go minus 1/2 times x dx. So that's our integral to solve. And this one's not so bad. This one doesn't require anything fancy like u substitution. We can just use section 5.3, 5.4 techniques right away and get this area. So first we take one antiderivative here, the one for x. This is going to be equal to x to the power of, add 2/2 to this, it's power 3/2. So multiply it by 2/3, then go minus, same idea here. This x, I'll put in a little bit of extra space and write in power 2. That means the power 2 is going to divide this 1/2, so it'll turn into minus 1/4. Then take all of that, the entire antiderivative here, we're evaluating it from 0 to 4, and our work is just about done. It's all just arithmetic function evaluations from here. So once we complete this, we'll know the areas between the square root function and the x/2 function, from 0 to 4 specifically. Well, any questions at all getting to this stage here? Okay, let's keep on going on this one. Again, it's not the world's worst antiderivative to have taken, so a nicer definite integral. We've seen much worse in section 5.5 already, but there'll be some tricky ones in these notes and this chapter altogether. So we'll be repracticing the substitution rule here and there as we go through chapter 6 as well. So first thing we're doing is just plugging 4 in for x to get 2/3, 4 to the power 3/2, minus 1/4 times 4 squared. Once we've used up the upper limit of integration, go minus. In principle, we need parentheses, but we're plugging 0 inside of everything, so everything just turns into 0. I'll write out the steps just for the sake of showing the pattern. It'll be 2/3 times 0 to the power 3/2. That's 1/4 times 0 squared, but again, all of that's 0, so we're subtracting one big 0 from that. So the answer to this area is going to become 2/3 times, I think we've done this one before, kind of have deja vu in this problem, but if you have to evaluate 4 to the power 3/2, one way to do this is rewrite this as the square root of 4 and write the result to power 3. Square root of 4 is 2, so it becomes 2 to the power 3, or value 8 altogether. So that whole amalgamation here is just times 8. Minus, this 4 cancels into the 4 squared, so it's just minus 4. So this becomes 16/3 minus, we can write this as a 12/3 to get the common denominator. And that finally gives us a dead-on exact 4/3 altogether. So area between the square root of x and negative x/2 on these bounds is an exact 4/3. Well, that's the idea of area between curves. Again, it's not the world's biggest, most exciting application to integration, but it's just extending on what we said before. For trying to find the area under the curve, we can extend to the new concept of areas between curves in this kind of way. Any questions or thoughts on running through the formula on this example here? Okay, well, for the next few problems on these notes, our whole goal is just to practice with this concept a little bit more. Sometimes we'll have a diagram like we see here. Other times the diagram is gone. It'll be up to us to produce the diagram to assist us with the integration. So these are kind of the nicer problems that it starts off, the homework in section 6.1, when a diagram is provided. So here's part A, kind of a nice diagram, nicely shaded for an area. Here's a diagram for part B. It's a little bit weird because it says x equals y cubed, x equals y squared. So we'll have a new idea on how to handle this one when we get to it. But first, the whole idea is to find areas between the given curves, and that's our area A we want to solve for. So to get that area, it'll be an integral from, first thing we need to find are, what are the limits of integration? The shading stops right here, right on the y-axis, so that means the limit of integration for a lower bound is 0. And then when we move to the right, the area stops right here. When this says x equals 2, that means the tick mark right there, that's kind of mistargeted. Right there is exactly 2, so the upper limit of integration is 2 here. Then we have an upper function, a lower function, and we just have to go upper minus lower. And you know, if you got those backwards, you took the lower function minus the upper function, your answer is not correct, but it's just off by a negative sign. You know the area has to be positive, so if you take off that negative sign and just say my area is this, just as a positive quantity, your answer will be correct if there were no other mistakes. So actually swapping upper and lower is not as big of a danger as it might seem. We just know we're expecting a positive area, peel off the negative sign if we ever see one, meaning we might have swapped those two functions. So now putting this together, we're going to take square root x plus 2. I'll write it this way, x plus 2 power 1/2 minus 1 over x plus 1 dx. So if we can get through that integral, our work is going to be complete. And it is kind of a tricky integral. Before we go to solve it, any questions on just putting it all together? Okay. Well, this one's a tricky integral if you're thinking in terms of section, say, 5.5, u substitution, because there's a function inside the square root function, x plus 2. There's a function inside the 1 over x function, 1 over x plus 1. But actually, this one is not necessarily has to be done by u substitution, which is kind of amazing in a certain sense. Let's write down some fast formulas that we have available to us, where we know that if we're taking the antiderivative of, say, square root of x, that would be the antiderivative of x power 1/2, which would then be x to the power of, add 2 over 2, so it's 3/2, divide by 3/2, multiply by 2/3, in other words, and add a constant. So if this first one is just x, that's the formula that you would take. It's more than that, it's x plus 1, x plus 2 rather, but that's still a relevant thought for this one. On the next one, what's relevant is if you have, say, something more simplified than that, just say a 1 over x, then this is the one that becomes the natural log of the absolute value of x plus a constant. This isn't just a 1 over x, it's 1 over x plus 1. So chain rule is actually relevant when we use a formula like that and check out the derivative. But there's kind of a miracle on both of these. Let's show how both of these formulas can work on this one. That kind of sidesteps u substitution. So you could rewrite this now as, let's take the antiderivative right here and now. Antiderivative of x plus 2 to the power 1/2 should be x plus 2, add 2 over 2 to the power like we did on the example above, so it's 3/2, multiply by 2/3. Now let's do a quick check on this one by mentally seeing what would happen if we differentiate. It is a chain rule problem, absolutely, because there's a function, not just a variable x, inside the power 3/2 function. But if you differentiate this, 3/2 moves in front, cancels with the 2/3, so that's gone. The new power is 1/2, one less because we're differentiating. And then we chain on a new derivative. We multiply by the derivative of x plus 2. But that derivative is 1. That means we really get the right function right here that we're expecting. This doesn't work every single time, but the reason this worked this nice of a way, essentially just using this formula up here, is because it wasn't like a 5x plus 2. If there was a 5 there, then when we go to take the derivative of 5x plus 2, there's a times 5. But in that case, we could just divide by the 5 to get the right antiderivative right at this step. So what this all says is, U substitution is a technique, is great, it's really important, but it is a lot of steps too, like we noticed in section 5.5. When you go to solve more and more integrals, we're always looking for a way to not use U substitution if possible. And so these will be a common things that we'll do later on, especially in Calculus 2 when these kind of integrals come up. So U substitution wasn't necessary on this one, and same exact idea on this one. Antiderivative of that becomes negative. Following this formula, we would say natural log absolute value of x plus 1. Then we want to mentally check this by differentiating. If you differentiate this, it's a chain rule process. X plus 1 comes down to the denominator without absolute values. We multiply by the derivative of x plus 1, which is exactly 1. So our work is done on this. U substitution wasn't necessary. But again, be really careful because for a lot of problems, it really is. If that's x squared plus 1, it's not a natural log. If there's more going on with this, U substitution might be necessary and so on. So we have to be very careful with these kind of problems. And just to reiterate that thought, if it was 1 over x squared plus 1 dx, that one is also not U substitution. That one turns into tangent inverse of x plus a constant. So see that table in section 3.6 for the inverse trig functions. That's where this one gets involved. The derivative of that function is the 1 over x squared plus 1. Usually we say 1 plus x squared instead. So integration is really finicky, but this one wasn't so bad to get through. We're just going to take this whole entire result, evaluate it from 0 to 2. Okay, so we're nearly done with this one. We just have to run through the final motions. Any last thoughts or questions on getting through to this step here? Okay, let's plug in our values. We're putting in an upper limit of integration 2 to start. So this will be 2/3. This is 2 plus 2, so this is times 4 to the power of 3/2, and that's deja vu. I think we've done that before. Yeah, there's 4 to the power 3/2. We don't need to keep doing that. We know that's 8. Definitely the number 8 at this point. Kind of curious that keeps coming up. Plug 2 here. This is going to be natural log of the absolute value of 3. That's just 3, so we can just write it in the normal way with parentheses right at this step. Minus, now plug 0 inside. 0 here is going to give us 2/3 times 2 to the power 3/2 on this one, minus the natural log of 0 plus 1 absolute value. That's just going to be 1 altogether. So natural log 1 goes to 0. There's a little bit more work to do on this term right here, but we'll get through that once we get to the next steps. We're about there. Let's start computing these out. This is going to turn into 2/3 times 8, as we've done a couple times now, minus natural log 3, minus, and this one's kind of a mess. If you left this as 2 times 2 to the power 3/2 divided by 3, I would say that's a decent step to take. Let's see if we can do a little bit more to clean that up. Exponent work does come up plenty in these kind of problems, so it's decent review work all on its own. So 2 to the power 3/2. I probably would do this one a little bit differently. Let's rewrite this as square root of 2 cubed. I think that's a better way to go for this particular version. 2 cubed is 8, so this is the square root of 8, which we could factor down as 4 times 2, and then rewrite as 2 root 2. I don't know if that's a big simplification, but if you want to take that, that's decent review all on its own. 2 to the power 3/2 is 2 root 2, and then minus 0 from the natural log 1 portion. So this is becoming a 4 root 2 altogether here. And now we have, from left to right, 16/3 minus natural log 3 minus, we can bring this together, 4 root 2 thirds And we're pretty much done at this step. If you want to, you can add up the fractions here and here. You have the least common denominators, but these aren't like terms in the numerator, like roots, rather. So I'd say this is a decent stopping point right at this stage. We've got the exact answer. If you want to put it in the calculator, that's optional. But this is the main thing I would be looking at for credit for this problem. We got it, folks. This is kind of a awkward constant this time. Not a nice and round, say, 4/3 like we've seen before. Area between these kind of curves, root x plus 2, 1 over x plus 1, on this domain from 0 to 2, is that constant. Bad idea, or a great idea to take, even in an exam setting, is put this into a calculator because we expect this to be a positive area. And it's not always easy to see if these are positive when you have strange constants like these. So let's see what happens when we take 16/3 minus natural log 3, then minus 4 square root of 2 thirds. It's a 2.35 altogether upon rounding. And that looks like it's about right then. So for that value here, I would have pretty good numerical evidence that that is the right answer. So that's one down. We have a few more to practice on these notes before we turn to volumes. Any last thoughts or comments getting through this one? Okay, so far, this is areas between curves in a nutshell. Major thing we're doing here is really just reviewing integration, sections 5.3, 5.4, and section 5.5 when it comes up. This one kind of has a new idea all to its own. Here, we have a variable x equals y cubed. That means y is actually the independent variable, x is the dependent variable. Everything's kind of just flipped around on this one. It's a strange kind of curve to deal with. And even though we could solve for y and write it in the normal way, y equals a function of x, y is some other function of x for both the curves, that's not always easily done or readily possible. So for this one, just for the practice of the technique itself, let's leave it in terms of the variable y as the independent variable, just to see how this goes. And here's one thought that you can take. Let me recopy the curve. Sometimes this is really just a matter of perspective. So if you imagine that this is x equals y cubed, x equals y squared, you're just interchanging the role of x and y, nothing more really. So if you flip this around, let me see if I can do this in a reasonable way. That's not the right way to do that. Let me try again. If you flip this around by going like, say, this, that's maybe a little bit better. Let's see if we can make it go like that. Still kind of weird. Let me see. Let me try one more time. Yeah, I was thinking maybe in terms of this. Flip it around to like that. I want to interchange x and y. Let me try one more time. Yeah, that's more along the lines of what I was thinking about. If you change your perspective to something like this, here's your x-axis, here is your y-axis. No, hang on, still not there. I should have practiced this before starting today. Maybe what I'm thinking of is really just rotating it. How about that? So if I rotate it in this way, maybe bring that back up. Yeah, I think that's how I wanted to transform it around. That took me a little bit of practice to see it that way. So here's a different way to think about it. Change your perspective, which is kind of looking at this inside out in a different sort of way. Here is the vertical axis. It just happens to be named x. Here's the horizontal axis, just happens to be named y. That looks funny, but this is x equals y squared. This is x equals y cubed, and that's a decent way to go. So we'll see it in two different kinds of ways, just looking at the original diagram or visualizing interchanging x and y in this diagram over here, which is kind of a good mind exercise to visualize that. So maybe the first one, let's focus on this diagram to see how it goes, because that's usually how we see things. If that's our diagram, we would say area is going to be equal to integrate from A to B. Well, the A and B comes from the horizontal axis. That's where the bounded area in blue here starts and where it ends. It goes from 0 to 1. So we're integrating from 0 to 1. And then what we need next is an upper function minus a lower function. And that's the upper function. Let me rewrite it because it's kind of hard to read when it's kind of been inverted like that. Upper function is x equals y squared. This one's the lower function. Down below here, the one in red, and lower rewritten is x equals y cubed. So we see upper function is this one. We can put that in first. And when we do this, we think of the dependent variable as the function itself. And that's the formula for computing the function. We bring in y squared in this way. It's y, not variable x this time, but that's because x's and y's have been inverted. Then go minus, same thing, subtract the lower function, that's y cubed. And for this, we're integrating on the y-axis from 0 to 1. So we would say dy this time. So we're changing the role of x's and y's in every aspect of the limits of the integration, the formula, and dx also became dy altogether. So kind of a weird trick, but if you're visualizing it this way, this is exactly how we did part A, just different names for the variables. So this is a good strategy if you like these kind of visualizations, if it's easy to imagine how it would flip around. Sometimes you can kind of rotate your head and see it the same way. But if you stayed with just this diagram right here, this integral is relative to this diagram as well. We usually think about integrating along the x-axis. But the variable x has been solved for on both of them, and it's inconvenient or impossible to solve for the variable y. We're just going to keep the diagram as is, and we're integrating on the y-axis instead. Integrating on the y-axis means we're going from 0 to 1, picking a dy value. We'll have a random value y that we pick as it goes from 0 to 1. And as y goes from 0 to 1, there's a little line segment here that moves along as y goes from 0 to 1 and moves along from up to here where it turns into a point, down to here when it turns into a point. And we would say that the lower function is the one that has the smallest x coordinate, except for where they match, have the same exact values. So that tells us this one is the lower function. So integrating on the y-axis, going from 0 to 1, gives you y equals x cubed as a lower function. We go here, we start at that function, we move a little bit higher, and the top function is y squared, so that would be the upper function. These kind of weird viewpoints for diagrams is kind of the new technique on this part B. That's something that we take a look into again when we're looking into in Calculus 2, dealing with surface areas, volumes, and so on. This is another thing that we sometimes do in these kind of diagrams. So not just a trick, this is something that's useful in its own right to integrate with respect to a different axis like we're seeing here. So now that we have this integral set up, it just boils down to find the answer on this one. The hard thing about these problems is sometimes just setting up the definite integral. Once you get the definite integral, the integration steps are usually go by a lot faster. So that's two ways to visualize, keeping the same diagram or re-visualizing it in this strange way here. Either way we take a look at it, it's just that integral. Any questions at all putting down that definite integral there? Okay, well, let's finalize this one, see what we get out on this. Antiderivative is not bad at all. We're just going to use the power rule twice. On the first one, copying a little bit of space, put in y. Power goes up to 3, so we multiply that by 1/3. So that's our first antiderivative. It's kind of relaxing when they go fast and we don't have to use a substitution rule. Then on this one, this becomes a y power 4. So we write it like that way, and with the extra space, multiply by 1/4, as we've done on the others. Then take this entire quantity, that's the antiderivative, evaluate it from 0 to 1. So this is now the fundamental theorem of calculus part 2 at this step. And the rest of this is just arithmetic from here on out. Plug in 1, that's just going to be 1 cubed. So that's 1 times 1/3. I'll just write that as a third. Minus, plug 1 here, 1 power 4 is 1, so that's just a fourth here times 1 for just a fourth. And the lower limit of integration 0 is really, really convenient. You just get 0 here, minus 0. Let's just write down a minus 0 this time. Usually we put down a third times 0 cubed minus a fourth times 0 power 4, just to show the pattern. But this would be a more typical thing that we might write down. You don't even have to write this down. If you don't even say minus 0, you still have the dead-on exact answer. So now it boils down to a third minus a fourth. We can rewrite that as 4 minus 3 over 3 times 4 to simplify these fractions. This tells us that this area is just a narrow 1/12, small 1/12 for this narrow segment here between those two curves. So that's one way to do the problem. Again, you could rewrite these functions, solve for y on both of them, and then do it like we did in part A. It's actually more work to do that. And like we mentioned before, there's plenty of curves where solving for the variable y is not feasible or impossible. So this kind of technique, integrate along a different axis, is a common one, not just used in calculus, but in other applied settings as well. Well, we did, folks. That's integrating along a different axis this time. Definitely a new technique. Any thoughts or comments on getting through this one? Okay, well, we have just one more problem to take a look into before we're done with these notes, the example number 2. I do have an application at the end of this one, but I didn't ask for this one in the actual homework assignment as a question. So we'll skip through this one unless anyone would like to see it solved. Let me know. I'll be happy to take a look into this one with you. It's a decent application for looking into the differences of amounts of rainfall for areas between curves. But this will be our main topic right here, this example 2, to help out support the homework. And notice what's missing this time. This time, it just says, find the area between these two given curves. It doesn't tell us what the limits of integration will be. We have no idea what these curves are going to really look like when we plot them together until we do. So there's a lot to work on to do on this one. And that's kind of a theme for plenty of problems in chapter 6. Coming up with the integral is sometimes the hard part, but once we have it, the integration steps go a lot faster. So we want to sketch the region that's going to be bounded by these two curves. So there's a bounded area here somewhere between the quadratic and the linear. Then find its area. And I've duplicated these steps as well for the homework. We need to show the steps finding the limits of integration. So maybe before we even sketch this, if we find the limits of integration, we'll know on what range we're sketching the functions on to begin with, and that helps us out a lot. So to find the limits of integration, we're just going to say, well, if y equals x squared minus 2x, and y is equal to x plus 4, there's two functions there, just equate them together. X squared minus 2x must then be x plus 4, once these two equations are on the table for us. And if we solve for this, that will give us our limits of integration. So this is finding limits of integration. Not a bad equation to solve. We can get 0 on one side and say that this becomes x squared minus 3x minus 4 equals 0. Then it's either the quadratic formula or factoring. If we factor, this will become an x and an x minus 4 plus 1. That seems like the most reasonable way to do it. And yeah, that looks like it pans out. These two constants multiply to -4, add up to -3. So that's the correct factorization. And immediately we have solutions. This implies x equals -1 or +4. Those are then going to be our limits of integration. And so this allows us to go to this step right here, actually sketch the region where the area is going to be bounded. If we want to just do the area right now, the trouble is it's not easy to tell which function is upper, which function is lower to get the dead-on exact area without being off by a negative sign. So this is going to help us make sure we have the exact area, not worry about being off by a negative sign. We're going to graph from -1 to +4. So that axis should do the job for us. I'll start with the linear function. That looks like the easier one to plot. Plugging a -1 there starts us off at 3. The scaling is a little bit different on my horizontal and vertical axis. I just noticed I ran out of space. So different scaling, but it doesn't matter if you change the scaling on one. We'll still have the right sketch. When we plug in 4, we end up at height 8. So 3, 4, 5, 6, 7, 8. About right here. And there's the linear function. Y equals x plus 4. Still don't know if that's the upper or lower one. So let's sketch this one as well. For doing a curve sketch on a polynomial like that one, next thought is it's not a bad idea to factor it. So y equals factor out x, you will get an x minus 2. This gives you x-intercepts. One x-intercept is at 0. The next intercept is at +2, so that helps us out. And because we set both functions equal to each other, we also have these points. The functions match at the endpoint here at -1 and the endpoint here at +4. So we really have a lot of points altogether. Let's maybe do one more evaluation. If you plug 1 inside that function, you would get 1 minus 2 for a -1. So this is the rough sketch of the quadratic. X squared minus 2x on this range looks about like that. And I need to rewrite where I put that y. Let me put it here. Y equals x plus 4. We now see that this one is the upper function. We can't just go off degree to determine which one's upper, which one's lower. So that might have changed our expectations on this one. Lower function, y equals x squared minus 2x. And what we want is this area for this strange shape, whatever it is. We might imagine maybe someone's building a swimming pool. They need to know how much material for a cover on that thing. Who knows? But what we do know is we can now find that area exactly. So we have limits of integration. We're going from -1 to 4. We have the two functions. So we can now put this all together and say area is going to be integrate from -1 to +4. Take the upper function, x plus 4. Subtract the lower function, x squared minus 2x. And that's our new integral to solve on these notes. One comment here is, when you go to solve an integral, you always want to simplify the integrand as much as possible. Not combine like terms just gives you a whole bunch of extra busy work when you evaluate from -1 to 4 on your antiderivative. That's completely unnecessary. So the more we do to simplify this is well worth it. So we're going from -1 to 4 of x plus 4 minus x squared plus 2x, which means this is going to be integrate from -1 to 4 of -x squared plus 3x plus 4 dx. Notice that that's basically what we had here, but the whole thing's been multiplied by -1. That's what we would have looked at if we moved all of the terms to the right. So now antiderivative of that thing is not so bad any longer. This is -1/3 x cubed on the first term. Next antiderivative, this will be a positive 3/2 x squared. And final one is going to be plus 4x. We need to evaluate that whole thing from -1 to 4. And it is tedious because now it turns into, even though it was just 3 terms, a whole lot of busy work on this one. Let's write down what it looks like on the next step. This becomes -1/3 4 cubed plus 3/2 4 squared plus 4 times 4, or just 16 for short. Then go minus, we do need parentheses, throw in -1 into all of these. -1 here cubed is -1, so that turns into a positive 1/3. -1 squared is just 1, so this is plus 3/2. -1 here will give us a -4. And that's still a lot of work to get through. If this comes up in a homework situation, it's reasonable at this stage, plug it into a calculator and give an answer out. Similarly, on an exam setting, you're not expected to crank this out, combine the like terms, get the least common denominators, all that kind of stuff. It's reasonable to put it at the calculator at this stage. So back to the calculator. Let's do that same thing. This would be -1/3 4 cubed plus 3/2 times 16 plus 16 minus third plus 3/2 minus 4. So it looks like it's a repeating decimal. I'll put it in as the fraction, 1/25/6. But I'm happy with either answer. So if you go that route, in fact, let's go that route. That's usually what you might see in your calculator. That's an acceptable answer. 20.83 repeating. So that's our area between these curves. Decent amount of work. Most of the work was setting up the integral to getting to here, and then running through the arithmetic stage. When you see these kind of questions in, say, the homework setting, possible final exam question, these are the steps to take. Equate both equations, get your limits of integration. Then you can sketch out the region. And if anything goes wrong, if we came up with a negative sign, possibly all that happened was we got the wrong function for the upper, the wrong function from the bottom. You can state your answer as that positive area, and that's an acceptable final statement to make. But we did it, folks. This is the conclusion to these notes. What we'll be taking a look into next when we come back on our Thursday's class tomorrow is dealing with volumes. So that's a whole new section. Probably this is a good stopping point for us. I don't think we can make too much segue with our remaining time that we have. So I'll turn it over to you folks for our last remaining time. Any last thoughts or questions whatsoever before we call it a day? Okay, well, have a great night, folks. On our Thursday's class, we'll take a look into section 6.2, possibly 6.3, depending on our pacing. But the major emphasis we're going to try to give is focusing on just the integration side itself. This is the major takeaway again for chapter 6, just more practice with integration. But have a great night. I'll see you all tomorrow.